It's a delight to have you, and over to you, Geoff.
Thank you very much. Thank you. It's very kind. You're very patient as well. I'm sorry. I was at Wolverhampton railway station 50 minutes ago and got a taxi. It's taken me an hour to get from the Wolverhampton railway station to University of Wolverhampton, which I didn't anticipate. Anyway, I'd like to look at what is high quality teaching and learning, if I might. There'll be a handout on the pack, and if you want the PowerPoints, you're very welcome to them. But it's going to be a relatively interactive sort of session. It's not just going to be a lecture. So I'd just like to give you fair warning that I'm about to explain a thing called co-constructivism. And I'm going to ask you in a moment to explain it to each other in pairs. And you will be asked to do either to explain what is co-constructivism or what does it tell us about how to teach after I've explained it. So this is peer explaining, right? So you'll explain one of those two statements to your partner in a moment, and she or he will explain back to you the other one, okay? So you're ready, you need to listen there, therefore, to be able to explain it yourself. When we learn, what happens is we make links between brain cells in our brains, obviously. And so if I ask you what's your address, you'll go to a part of your brain and you'll read a whole lot of little interconnected brain cells. You'll read that off as 14 the Avenue, Walsall, or wherever you live. It seems incredible, but there's no pen and paper in there, there's no hard disk. So whenever you've learned something, you've actually made a little network of interconnected neurons, okay? And so that's the learning process. So when you teach your students something, they're in the process of forming this understanding, of making these little links. The meaning of what you teach is encoded by the student in their brain in the form of these interconnected neurons. And this meaning, of course, unfortunately, has been created by them. It is therefore full of errors, omissions, and all sorts of misconceptions. And so consequently, the teaching learning process involves you in requiring the student to form an understanding, not just enabling them to do it if they want to. Right? So I could have just stood up here and lectured to you, but I said at the beginning you're going to have to explain something in a moment. And that's given you a purpose for listening, as it were. So if I ask you to explain something to somebody else, you've sort of got to form an understanding of it in order to explain. Yeah? You're forced into it. But if I say, listen to me while I explain cash flow, or whatever, there's no requirement that you form an understanding. You could be thinking about the back line of Manchester United. You know, you could be thinking about what happened to Mandy in the lavatories on Friday night. You know, there's no necessity that you're focusing your attention on making an understanding that I want you to make. And so this process of forming an understanding is really quite a complex process, and we sometimes forget. We sometimes forget how complex it is. When the student walks into your classroom, they've already got some prior learning, and I've got that in black on the left-hand side there. It's obviously a very, very imaginary diagram, this. And the new learning ideally must be linked to what they already know. I mean, that seems obvious, and we'll see reasons for it in a moment, very, very directly. But the important point is the student makes this understanding. They do not remember what you say. If you ask them the next day, what did I explain yesterday? They will tell you in their words, not yours. They don't remember your words. They don't remember your understanding. They've got no access to it. They remember the understanding they created. And this is called constructivism. Sometimes there are various names for it. And the modern term for it now is sort of co-constructivism, because the trouble with constructivism by itself is it's a 1960s idea that a lot of teachers thought the best thing to do was to leave students to make their own understanding without any interference by the teacher, which is about as potty an idea that education's ever managed to come to. But we now realise the teacher and the student must work together to form this understanding, to construct these interconnected neurons that encode the meaning that you're trying to give your students. So you have to work together. It's what you do and what they do which decides whether this has been made. Now, a lot of people think that students just remember what you've taught them. I wish it were true. I really do. And I've got some proof that they don't, just in case you need persuading. This all comes from genuinely, this is absolutely true, these statements came from examiners who'd marked GCSE biology a few years ago now, so the syllabus has slightly changed. In order to understand this, you need to understand a few things. There's a thing called an amoeba. Do you remember amoebas? They're a sort of blobby type, very, very simple life form. And they sometimes form a shape. They don't have fixed shapes, they're just a sort of blob. And I'm not a biologist, so I'll probably got this slightly wrong, but they sometimes make a shape that looks a bit like a foot. It's called a pseudopodium, right? Now, pseudo means not real, a podium means what you stand on, leg, right? So it's like, they make a sort of pseudo-podium. And the way they move is to make this shape, because they start off with this shape, then they make that shape, and then they go back to that shape. And in this way, they move around and they eat and things like that. Okay, here are some students' understandings of biology, okay? Question 1 on this GCSE examination. Name a common disease of cereal crops. Okay? And one student answered, wheat germ. Well, you can see where they're coming from, can't you? Yeah? What happened here was they heard about wheat germ and they thought, well, that's obviously a germ that wheat gets. Makes sense, doesn't it? How do mammals keep warm in cold weather? Well, one student answered, revealingly, I think, they wear cardigans. Now, I'm not putting fun at these students. They're making it up. Yeah, they're making it up. This student thinks that mammals is human beings. Well, it's not that far off. Human beings are mammals, but it's not quite right, is it really? They make up their own meaning. Did the biology teacher tell that student that mammals keep warm by wearing cardigans? Actually, she might have done at one point, or he. Yeah, but obviously not entirely. That was not her entire explanation. How does an amoeba move? The amoeba throws out a pseudopodium and runs after it. How does an amoeba feed? The amoeba picks up its food using a false leg. Right? This is my favourite, because it's not even school learning, really. Name a, every year they put one question in just to make the students feel comfortable, right? Everybody's going to get it right? Name a food suitable for pickling. This is screaming for onions, isn't it? Pickled onions, probably. Okay. Name a food suitable for pickling. A Branston. Well, you go into a larder, you see Branston pickle, you see damson pickle, you see pickled onions, and what do you assume? Clearly the Branston pickle is pickled Branstons. I mean, it's sort of obvious, really. These students are not being stupid. They're making it up their own sweet way. And the problem we have as a teacher is that when students form understandings, they are inaccurate. Now, I've got weak students in GCSE biology. Is this any different for strong students studying mathematics at university? I don't think so. You could get 2 professors of mathematics and you could say to them, I want you to alternate and to say something about prime numbers. And sooner they'll start off with the obvious stuff, and eventually they'll run out of things to say. Eventually, one of these professors of mathematics will say something, and the other professor will say, no, I don't agree with that. Now, we're talking maths here. There are right answers, there are wrong answers. How can 2 professors of mathematics disagree? They do, quite commonly. How can they disagree? Because they formed their own understanding of their subject. And one is bound to know a little bit more than the other, and there'll be a difference of opinion about something or other. Yeah? So don't go thinking that any human learning is going to be perfect for us. No, thereby it hangs a very long tail. To do with sort of politics and religion and so on. But the thing is that human learning is human-made, and it will have human faults. Okay. It's not enough that the student forms an understanding. They must also link it in a way that forms meaning. So here we have, those exams that they give students in schools at the age of 7, 11, and 14, or we used to, and there were 2 questions. Have a look at those questions in red. They were on the same examination paper, and the students were answering them within seconds of each other, or certainly minutes of each other. The first one was divide 235 by 15. That's a divide sign, not a plus sign. It'll come out very well. The next question is identical, actually, but it's in words, and it says, if a gardener has 225 bulbs to place equally in 15 flower beds, how many would be in each bed? 80% of students could do that, but only 40% could do that one. And the reason was that the students didn't know which mathematical operation to use. They saw 225, they saw 15, and they said, ooh, think I'll add, think I'll multiply, think I'll multiply 15 by 2 and then subtract. They had different notions about what they should do. Why is that? What's going wrong? Well, one of the answers, I think, is that when we this is what's going on in the student's head. This is the construction that the student is creating for divide. Yeah. So let's have a student called Joe. Yeah. Here's her division concept. Yeah, it'll be more complicated than that, obviously. Here is a cutting up concept. Now, all junior school kids will have cut bits of paper up. And if the teacher says, look, you just cut that piece of paper up into 5 pieces to make our Christmas decoration or whatever, yeah, you've cut it up into 5 pieces, it's like dividing by 5. Now, what we're doing now is we're taking a concept the student has walked in with, they've all cut bits of paper up, and we're saying division, mathematical abstract concept, is linked to this cutting up concept. Yeah? And that's good teaching. Because the student now will have a bit more, if you link those two, and tell the student that division is really just cutting it up. When we divide by 4, we're cutting it into 4 bits. That's what we're doing. Once the students have got that, not only do they understand division, they're able to use it. It becomes functional as a piece of learning. Also, some maths teachers will teach students about sharing. You might think all students experience this explanation. They don't. Otherwise, you wouldn't have had the trouble we saw earlier with the 2 different questions being answered in 2 different ways. So sharing out sweets. I've got 12 sweets, I've got 4 kids. How many is each going to get? If we do it fairly, we're dividing the sweets by 4. So, So when the students get that, and they see a link, and we're talking here about a physical link in the student's brain. Teachers change brains physically. Right? You are changing physically changing the brains of your students. But the student doesn't understand division until it's linked to what they already know. And the same goes for all learning, for absolutely all learning. You've got to start with what the students have already got and link the new stuff to that. And we all try and do it sort of, but we don't realise how mechanically vital that is. Because if the student hasn't got a physical link between those, then, by the way, we sometimes call that going from the abstract, we sometimes call that going from concrete to abstract, and that's absolutely the best way to learn. We all learn best from concrete example up to an abstract concept. So if we've got this division concept here, there's Joe's division concept there. Here's the learning she walked in with about cutting things up. Here's the learning that she walked in with about sharing things out. If you link those, then she can reason from cutting up, if I cut it up into 4 pieces, that's like dividing by 4. That's reasoning. Right? That's understanding. That is understanding. But if you go the other way, and also from the sharing out, if you've got to share it out amongst 15 flower beds, then, gosh, we're going to divide by 15, yeah? So the student now has a meaningful concept for division. It's not go to that thing on the calculator that's got a line with 2 dots and press it. It's now a meaning for this division thing. Consider that question again. The gardener's got it's got 225 bulbs to place equally in 15 flower beds. What should the gardener do? If the student says, hey, this is a cutting up question, she'll know to divide. Yeah? If the student says, hey, this is a sharing out question, yeah, she'll know to divide. But unless she's got that link, unless she's formed a concept for division linked to prior learning in a way that's mathematically sound, she's not going to have functional learning. And one of the worries I have is that when we teach students mathematics, I'm giving a maths example here, but I could have chosen any subject on the planet, just that we wouldn't all be familiar with it. So I'm not picking on maths teachers here. We all have the struggle of making meaning. In a way, these red links here are meaning, yeah? Something I don't really quite fully understand yet, linked to what I already know. If you go to a dictionary, it does exactly the same thing, right? The student goes to a dictionary, looks up cosmopolitan. What does it mean? Right? Doesn't know what the meaning is, and finds cosmopolitan described, explained in terms of words she does know the meaning of. Yeah, that's what meaning is. Meaning is a link between something and something you already know or have experienced and so on. So that link is meaning. That we're actually physically making a meaning link when students get the idea that division is sharing or division is cutting up. Okay, so we need to be able to go both ways. We need to be able to say, hey, if I divide, that's like cutting it up, isn't it? We need to be able to say, oh, when I divide, that's a bit like sharing in a way. But we also need to say, hey, I need to share these bulbs out between these flowers. Oh, that's a division. Yeah? So that's, that we need to go both of those ways, as it were. And I conclude from this, hopefully, that we've got to set reasoning tasks. It's no good just getting students to go through the processes that get the right answers. No doubt, all those students who did the 225 divide 15, they've gone through lots of class practice where they've used a calculator and punched in the right numbers and got the right answers out. But what does that tell us? Unless the student understands what they're doing, unless they've got a reasonably deep understanding of it, it's not really a meaningful thing to have done. So that's what we're trying to get. We're trying to get new learning which is linked to present learning, and we need so that we can go think both ways. Because literally, when we think, little electrical and chemical signals move around these neural pathways, these neural connections. We don't really understand the detail of it, it's phenomenally complicated, but we do know that that is what is going on. So to sum up then, when we're trying to form understanding of students, constructivism or co-constructivism is a better term nowadays, I think, so that we get away from that 1960s idea that we just leave students to make up their own meaning and sit in the corner while they do it. Sort of. Instead, we have this co-constructivism. The idea is we want our students to form an understanding, and we want it to be linked to what they already know. That means we've got to set tasks that require the student to form an understanding. Talking to them doesn't require the students to form an understanding. Asking the students to explain something to their peer does. They have to form an understanding of some sort. It will be, imperfect. If you ask them to, say, do an explanation, or say, write about it in your own words, or whatever. So, or say, here are 15 maths questions on cards. Yeah? I don't want you to do these questions. The students like that. What I want you to do is I want you to put them in piles. They're word questions. Look, this one here, it says, a gardener's got 115 bulbs and he's got 14 blah, 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 yeah? And there's another one. We've got 79 people. We've got taxis that will take 5 people a go. How many taxis do I need to get them all to the railway station? Well, you know, a whole lot of questions. I don't want you to do these questions, but I'd like you to, if you're going to solve them by adding, I'd like you to put them in one pile. If you're going to solve them by dividing, put them in another pile. If you're going to solve them by subtracting, put them in another pile. If you're going to do it some other way, put it in another pile. That sort of thought process where students are actually thinking about their mathematical reasoning and using mathematical reasoning is really powerful. And the same for every subject. We've got to get our students thinking in terms of these links. Okay, so co-constructivism then, which is really all learning. I'm not just talking maths, I'm not just talking primary, I'm talking all learning at any academic level in any subject. This is anatomical stuff. It's absolutely common to all learning processes. But if we want really good learning from the co-constructivist point of view, there are 4 characteristics I think we need to look for. Yeah? The one is that we've got to require the student to form a construct. It is not enough to give them the information. Listen to me while I explain. Watch this video. Because that doesn't require them to form an understanding. It only enables them to do so should they feel like it. Yeah? The other thing is we've got to provide a check and correct, because the one thing we can be certain of is that these constructs that the student has made will be wrong, because they made them. There will be errors in them, there will be omissions in them, yeah? Branston pickle is pickle Branston. Yeah, there'll be misconceptions in them. We need to discover those and we need to put them right. In the lesson, ideally, where we're teaching that concept, not in a test 2 weeks later. While we're teaching it, we need to discover those misconceptions and put them right immediately or as soon as we can. We ought to leave reasoning. We ought to ask reasoning questions. Daniel Willingham has written a lovely little book called something like Why Kids Don't Like School. And it's a summary, actually. It's not a good title for the book, actually, because partly because he never answers that question. But his main reasoning here is that it's basically he's looking at cognitive psychology and trying to say what teachers can learn from it, although he is a cognitive psychologist rather than a teacher, as you can tell if you read between the lines. It's still a very good book. He says, regarding this, he says, learning is the residue of thought. I'll write that down. Learning is the residue of thought. If you think about something, you'll have something left over, residue, and it's what you've learned. If you don't have to think about it, you won't have learned it. Yeah? There was a vehicle in front of you on the way here with a registration number. You might well have seen it. You won't be able to remember it. Because you didn't have to think about the registration number on that vehicle in front of you. Yeah? You just didn't have to. So it's gone. It's out of your memory if it was ever in there. What we remember and what we understand are things that we've thought about. And the deeper we think about it, usually, as long as the thinking's reasonably productive, the deeper we think about it, then the better we've learned it. Okay, so we need activities that require the student to form an understanding. We need activities that check and correct that understanding. It doesn't have to involve the teacher. It could be peers working together, it could be self-checks and so on. We'll look at some examples in a bit. We need reasoning to go on, and ideally, we want a bit of fun. We want the activities to be reasonably enjoyable. We don't want it to be too dry and boring and repetitive. So, which of the following methods are best from the point of view of requiring the student to form an understanding and requiring reasoning as well as reproduction? So the students are actually thinking about the topic and therefore they're going to learn, because thinking is the residue, learning is the residue of thought. Okay, so here are some methods. I've got reasoning. What does it require? The formation of constructs, or does it just facilitate it should the student want to? Can I ask you to work in pairs? Have a look at that. Which ones do you think are going to be best from the point of view of requiring reasoning and requiring the student to form a construct. In pairs, just give you a couple of minutes. Yeah?
Those four in the top right corner.
Those four in the top right-hand corner, watching a video, reading, copying and pasting relevant material, surfing the web. Okay. Yeah, I think pretty much agree with those. Those aren't particularly hot, are they? They might make the student reason, but they probably won't. If you ask a question, though, right, look at this website and tell me what are the main reasons why we use hydroelectric power. Well, because you require the student to think about the topic they're reading, then you're more likely to get reasoning going on, possibly. I think pretty good. Discussing in groups. There's a problem with group work in that students can be passengers. But you can overcome that problem if you just choose who will answer on behalf of the group. So you've got 3 students and one of them's a bit lazy, and they know I might choose her, yeah? The other 2 will sort of perhaps do the thinking work, but she's got to be prepared to give the answer for the group. And if she gets it wrong, the other 2 students in the group are cross. Yeah? Because apparently the group's answer has been displayed to the class in an unsatisfactory way, or it was an unsatisfactory answer. So don't ask for volunteers. Get your students, nominate students to give you the answers in group work. Reading, it's not too bad, but have you ever read a paragraph and then got to the end of it and thought, I didn't understand that. I wasn't even listening to what I was reading. I was thinking about what happened to Hillary in the lunches on Friday night. I better go back and read it again. Yeah, so reading doesn't even actually require understanding to be made, a construct to be made. But if you say, read this and answer these 4 questions, the student gets to the end of the reading, tries to answer the 4 questions, finds they can't, goes back, reads it again, and looks for answers for those 4 questions. So that's going to require them to think about it. So depending exactly how you do it, but those could be okay. The other ones are pretty good, I think, on the whole. If you've got to explain something to somebody else, you've got to have formed an understanding of it, really. There's no way out. You can't wriggle out of it, really. And same with writing notes in your own words. If a student writes her own notes, then it's going to help them learn. Okay, I asked you at the beginning to be ready to explain one of these 2 things. So I'd like to get into pairs. Could be 3s, you've got odd numbers, If so, the 2 of the 3s can do the second one, because that's harder, I think, probably. But if you get into pairs, and if you're on that side of the lecture theatre, can you take what is co-constructivism? And if you're on that side of the lecture theatre, can you take what does it tell us about how to teach? I'm going to give you 1 minute to prepare what you're going to say. You're allowed to make notes. And then I'm going to give you a minute each to do the explaining. So we've just got 3 minutes to do this. 1 minute for you to think. Get into your group and think. Okay. Can you do your explaining now? Start off with what is co-constructivism, and then the person who is doing what does it tell us about how to teach can pick up. Got a minute each. Okay, over to you. Got a minute each. Okay, stop it there. Here are, you could say a very great deal about this, but here are 3 points for each of those explanations that I hope to see there. That students make their own meaning. They don't just remember what you said. They make it up. Yeah? The learner encodes meaning in construct. Yeah? So they form linked sets of neurons, and that's how meaning. Interestingly, it's not words that are encoded in that way. It's meaning that is encoded. That's a very interesting distinction. If I ask you to describe to me a film you saw last week, you'll explain it in your own words. It won't be in the words of the screenwriter. It'll be in your own words. If I then leave you a day and I ask, could you just go over that film again? What was it about? You will then explain it again using different words, using different sentences, using different paragraphs. Now that's miraculous when you think about it. How is the film stored? In your memory, if you don't use the same words to express it on two separate days. And the answer is, it's the meaning of the film you store. And the same goes for concepts in, that you teach your students. They don't normally remember a string of words for a concept. They might do, if you force them to. But they'll usually actually remember a meaning, and they will express that meaning in different ways on different days. And the reason is that the brain actually has only been working with language for about 200,000 years. And that's nothing in terms of evolution. Prior to that, for millions and millions and millions of years, the mammalian brain evolved without language. And so we tend actually to think in what Steven Pinker calls mental ease. He calls it, as in a bit like Japanese, mental ease, mental language. We encode the meaning. We don't encode the words. Next one. New learning is built out of old, onto old, connected to old. And if it isn't connected to old, it's meaningless. Yeah? When my daughter was about 5, I won a number of pints at the local pub by saying that my 5-year-old daughter, because I was a physics teacher, I said, my 5-year-old daughter, she knows Newton's third law of motion. And they'd say, rubbish. So I'd say, I beg your pardon. And they'd say, usually say no, but sometimes they'd say yes. And Gigi, age 4, 5, she would say, to every action there's an equal and opposite reaction, and I'll be a pint better off. However, ask her, what does that mean? And we're in deep trouble. Yeah? So this is the distinction between rote learning, in the sense of learn without understanding, and deep understanding. That's not to say we shouldn't learn by repetition. It's the only way, actually. If you want to learn lines to a play or a poem or times table, repetition is absolutely fine. But if your student says 3 4s are 12, beware whether they understand it. Because if you say to them, I've got 4 taxis, each has got 3 people in it. How many people are there? And she goes, 1, 2, 3, 4, having just told you that 3 4s are 12, yeah? And then says 13, you know you're in trouble. Because she's learned the tables without understanding them, yeah? She's got to understand that 3 4s are 12 has a meaning, yeah? She's got to link it to little groups of 3s and little groups of 4s in her brain, perhaps. And the same, I'm talking primary here, but it's the same as the principle identically for higher order learning. What does it tell us about how to teach? Let's use methods that require constructs to be made. Let's not just tell students stuff, show students stuff, get them to watch videos, get them to look at websites. That may or may not require a student to form an understanding. And one way of overcoming that difficulty is, before you present students with information, is to give them a task for it. I did that with you. I asked you, to explain these things I was about to explain. But I could have asked you some questions about it and said, I'm about to explain cash flow. Here are 5 questions. Let's look at these in advance. Eventually, you're going to be able to answer those questions. And while I'm explaining, get ready to answer those questions. Then the student's thinking about it. And remember, learning is the residue of thought. It's what's left over after we've thought about things. So use methods that require constructs to be made. Set tasks that require reasoning, not just reproduction. Not just 3 4s are 12, but questions that require students to think. Here are some cards. So I'm going to solve that by a plus or a minus or a division. Students that need to be asked questions like why and when and how and things like that, not just to repeat back what you've told them. Check the constructs. They will be wrong. Yeah? They will be wrong. So check them. And why not use peer explainers as a little example? But there's millions of methods that require students to form an understanding and get a bit of feedback on them. I don't know whether you corrected each other's explanations just now. I could have asked you to, and it would have been a useful thing. But I'm checking your explanations now. Yeah? And so we've gone around a cycle of getting you to form an understanding, and now we're checking it. Yeah? And I'm hoping your construct for co-constructivism is being improved by looking at what I would have hoped you would have said when you explained it. I'm just going over the key points right here. Okay. How can we make methods below, which are very, very common and we can't avoid them, how can we make them co-constructivist? Well, there is a very simple way. I've just said, really, set goals in advance, yeah? You're going to have to explain this question when I've finished explaining cash flow. You have to answer this question. Or when I finish describing cash flow, I'm going to ask one of you to explain this and one of you to explain that, like I've just done with you. Or you've got to write it in your own words, yeah, whatever. You need set a goal in advance, then do the demo, then do the watch the video, then do the teacher talk, and then you just need a minute. You say, okay, now answer that question I gave you at the beginning. And what that does, it's called setting goals in advance. It's a teaching method that's been trialled hundreds of times and comes out very, very well in comparisons of rigorous trials of teaching methods in classrooms. Setting goals in advance, yeah? I wish I'd known about that when I started teaching, because for decades and decades I told students stuff, and then I said, now I'd like you to do so-and-so, and the students would look at so-and-so and they'd say, bloody hell, that's hard, I wish I'd been listening. And instead, what I should have done, I now realise, is set the goal first, then do the explaining, and then say, here's your goal again, off you go, do it. A minute, 2 minutes, but you've increased the concentration much and the focus on the things you want them to learn far better by that task. Okay, so I've spent a lot of time looking at the teaching methods that do exceptionally well in very, very rigorous trials, and I've noticed that if you look at cognitive psychology, if you look at trials in classrooms, sometimes called randomized control group studies or trials, RCTs, if you look at those two bodies of research, which involve completely different people, one looking at cognitive psychology, the other looking in classrooms at various teaching methods that are used, you find there's an awful lot of overlap between what they suggest or what they say works well. And a lot of the methods that work really well do the following. They set a challenging task, right? So explain this, yeah? Write your own notes on that. Make a mind map which summarises this topic. They set a challenging task, which is obviously that task is focused on the objectives for the lesson. It's not any old task. It's a task that focuses the students' thinking on what you want them to learn and the key points about what you want them to learn. So the purpose of the lesson informs that task. Yeah? That sounds like an obvious point, but it's amazing how many lessons for which you could say that isn't happening. But that's another tale. Because you've set a task that requires the learner to form an understanding, they do. Here it is. Yeah? They make their own understanding in their brain, but it's wrong. Yeah? Branston pickle is pickle Branstons, right? So we've got some stuff, but it ain't right. So what do? We can't look inside their head, but we can ask them to do a task, answer a question, make a mind map, design an experiment, whatever it would be, depends on the topic, obviously. You can set them a task that requires them to use that construct. And we can then look at their work. And we can say, oh, we've got that bit right, but that's not right, is it? Yeah? So we use their work as a window into their understanding. Yeah? I'll say that again. We use their work as a window into their understanding. And every student's understanding will be different because they made it up. They linked it to those different bits of prior learning that they had. And when the student's work is, can then be used by the teacher, I mean, the teacher can ask a question, get an answer, and realise, hey, that student doesn't quite understand that point. Yeah? And then can say, does anybody agree with that answer? And a whole lot of other hands go up, and the teacher thinks, bloody hell, half the bloody class don't understand this point. And then they can step back and say, let me explain this again. Yeah? But what they've done there is they've used the student's work, in this case it's just a verbal answer to a verbal question, They've used the student's work to provide feedback so that the teacher can change the way they teach to improve those forms of understanding. But the learners can do the same. A learner, you can ask students to look at each other's explanations of something and to improve them. Peer assessment, just very informally. Check each other's notes, have a look at them, you've got 1 minute. Say one thing you like about what your peer has written. Say one or two things that would improve it, or whatever the numbers are. But try and get some sort of suggestion for improvement in that work that the student's done. Same with the mind maps. So what we're after here is improvement. So this is a feedback loop, but it's a genuine feedback loop in that the student forms understanding, expresses their understanding in their work, and then the teacher and other learners improve that construct by saying, no, it's not quite like that, it's like this. And that ideally needs to go on very quickly, verbal question and answer, peer check in class, rather than you taking their work away, marking it, giving it back a week later. We want this cycle to go as quickly as possible, as quickly as we can manage. Okay, or as quickly as sensible anyway. Here's a little teaching strategy. It raises students' performance by about 2 grades on average. This has been trialled hundreds of times in real classrooms. And when we get some students to produce these mind maps in this way, they do about 2 grades better than students in an identical class, taught in an identical way by the same teacher. You lot will get 2 grades worse. So if I mark the work that students do, A, B, C, D, E, a student in here who gets a C grade would have had an A grade in this group, because this group made a mind map in this way. Very powerful. We know that these methods work really well. Have a look at this from the quality learning cycle point of view and see how it works. Are there any loops? Where are the loops that are improving the student's understanding? This is how it works. The teacher presents some new material. So this is an activity after you've presented new stuff. Okay? Then the teacher asks for a mind map. They say, okay, I want everybody to make a mind map. And ideally, they will have set this goal in advance. So at the very beginning of the lesson, they will have said, I'm going to ask you to make a mind map in about 25 minutes after I've finished explaining this. And we've watched a DVD and so on. So get ready to make this mind map. So the teacher asks for the mind map, the students create it. But then when the students are nearly finished, each student leaves their mind map behind on their desk, gets up, looks at everybody else's. But the purpose of doing this is to find things which the other students have thought of or explained well, so that they can sort of harvest ideas that will improve their own mind map. It's not to assess each other's. So they get up, say I'm a student in your class, I get up, I have a look at somebody else's mind map, I think, well, this is pretty much the same as mine, oh, this is much better than mine, oh, it's got a bit on here about sound, so I haven't got that. I better remember that and go back and improve mine. And so I go back and, after looking at a few of these, I go back and I improve my mind map. Okay? So I improve my mind map, and then the students self-assess or peer assess against some criteria which the teacher provides. So the teacher picks up some key points that ought to be on the mind map and says to the students, have a look at your mind map, have you got that? Yeah? And the students might do it as a self-assessment, or they might do it as a peer assessment. That process will have a massive impact on students' learning. Have a look at it from the quality learning cycle, as I call it, this one here, high quality learning or quality learning cycle. Can you see how you require the student to form an understanding? Can you see how that understanding is improved? How often is the understanding improved? Just in pairs, have a look at that and see why it works, Just a minute or two there. The student is asked to form a mind map, and they're given warning in advance that they're going to create it. They listen, they form an understanding as well as form the mind map. Yeah? They then look at everybody else's mind map and they say, oh, I've missed a bit there. Oh, that's a good idea. I'll put that on my mind map. And they improve their mind map. But they also improve their construct. Yeah? Well, in fact, the mind maps of less importance, really. What really counts is what's up here, not what's on paper, really. Then the teacher says, okay, now you've improved your mind map. Have a look at my key points. 12 key points. Are those all on your mind map? And the students say, oh, wow, I haven't got number 6. Better write that in on my mind map. But they're also writing it in on their construct. Yeah? And so the teacher and the student together are constructing the student's construct, if you like. This is why it's now called co-constructivism. Yeah? Together the teacher and the student are trying to form an understanding, and we're checking that understanding. We're improving it as we go. Okay. There are lots of high effect size teaching methods that work, and they all seem to relate to this cycle. There's a handout with a cycle on it, and you can get the PowerPoint as well if you're interested. But here's a method that's got a very, very high effectiveness, and it actually takes less time. It saves more time than it takes. The teacher getting the students to recall the prior learning that they will use in that class. So, if we go back to this, these black bits, are they there? Are they firm? The teacher checks them, the ones that the new learning will be connected to first, and then teaches the new stuff, so that the relevant prior learning is ready to be connected to, as it were. That's got a tremendously high effect size. Setting goals in advance, that requires a student to form a construct. Students writing their own notes and then peer assessing it, and then the teacher checking it. Very, very powerful, about the 2-grade leap again in these hundreds of rigorous trials. I've written them all up in my book, Evidence-Based Teaching, which sort of follows on from teaching today. Class discussion of students' answers. 2 maths students put answers up on the board. One of them's pretty much okay, the other one's not so. But it's a common mistake. And I say to students, okay, looking at Paul's answer here, what have you noticed? Anybody got any thoughts about what's right and what's wrong about that? And the student says, I think it should be a minus sign on the second line. And I say, thank you. Does anybody agree with that though? Should it be a minus sign on the second line, Paul's? You don't think it should be? Why do you think it should be a positive sign? Okay, thank you very much. So some of us are saying positive, some of us are saying, who's right? How do we know? My time. I've got 6 statements here. This is called Diagnostic Questions. This method I'm about to use with you. And it does exactly all the same stuff I've just been talking about. Here are 6 statements. If you've got time, and I absolutely understand if you haven't, you need to go, that's fine. But if you've got time, look at those 6 statements. Which one's true, which ones are not true? Some of them are true, some of them are false. So there's no real pattern or anything. In pairs. Which of those 6 statements are true? Which of those are not? Okay, have a look at those. What I should have done actually is to ask you to form answers to those questions by yourself first, and then comparing 2s and 3s. That would have been a more powerful approach, but I'm running out of time here, as we all do. Students encode their own meanings in constructs, not the teacher's meanings. Could you show me your answers by putting a thumb up if you agree and a thumb down if you disagree for that one? Almost everybody's putting their thumb up and you're absolutely smack on. Number 2, you notice I'm getting feedback from that as to whether you've understood it, yeah? So, student meanings are wrong because of their low ability. Thumbs, almost everybody thumbs down, you're absolutely right. High ability people make these misconceptions while they learn. Everybody does. Feedback in the quality learning cycle means teacher comments on students' work. Thumbs? No, it doesn't. You're absolutely right. Thumbs down everywhere. I think you're all doing very well on this. I'm surprised at this time of life. Very good. Self and peer assessment are bound to be inaccurate. Thumbs, you all disagree with that. Well, I think you're wrong there. I think it is bound to be inaccurate, but it doesn't matter because it will force because it forces the student to form an understanding. Most of the time they're right, If they don't trust each other, they just argue more. And we remember about what we think about, yeah? So it will be inaccurate. So a teacher check afterwards will be helpful some of the time anyway. But it doesn't matter, but still use it. It's extremely powerful, very, very high effect size, even though they're talking rubbish. We don't quite understand why. Okay. Co-constructivism requires the teacher to mark students' work carefully and frequently. Thumbs? No, it doesn't require marking. That's the right answer, because the students can check each other's, they can check their own, it can go on in class, the students can look at your key points and say, oh, I've got that one, but I haven't got that one. They can self-assess, so it doesn't require necessarily your marking. Last one, co-constructivism is the same as constructivism, really. What's the difference? Most of you got thumbs down, which is brilliant. What's the main difference between those two? Absolutely. Constructivism is the student alone, pretty much, whereas there's a lot of teacher involvement in co-constructivism. The teacher's always checking, correcting students' constructs and forcing the students to change their learning. Thank you for your time and attention. Thank you.